each page to another page. A hidden Markov model is a structure in which you have observations, and it's called hidden because these state descriptions may not be visible to the observer. It's these observations that might be visible to the observer. And in the hidden Markov model, these would correspond to sort of causal conditions that we talked about last Tuesday, or last Tuesday's lecture. And the probabilities that you need to specify here are the probability of S sub 0, the probability of the various states at S sub 0, the probability of transitions, and again, it's sufficient to, in a Markov model, to specify the probability of a state in any S sub I to any S sub I plus 1. So you could specify these probabilities here as doing that. You note, if we just interpret this as a Bayesian model, the probability of state 1 is independent of an observation O sub 0 conditioned on S sub 0 being its prior state or its parent. And then we've got to specify probability tables here, the probability of O sub I given S sub I. And so, again, this is augmenting the Markov model with observations. And what we're very often going to want to do with a hidden Markov model is what is called filtering, given a set of observations. So these are observations about that are corresponding to each state, but are not the state themselves. So if we want to predict, or if we want to estimate or compute the probability of S sub 4 here, that we found ourselves in S sub 4, given observations of all prior states, not the states themselves, but observations made at those prior states, O sub 0 up to O sub 4, the current observation. So estimate the probability of this conditioned on these only. Then that is a process which is used quite a bit. One way that you might do it in this case is, again, if you go back and you watch the video on computing probabilities, you know how to compute conditional probabilities in a Bayesian net. There's nothing different that you have to do to compute these probabilities and express them in terms of probabilities that are actually found in probability tables beyond what last Tuesday's lecture discussed. So let's say that we want to compute the probability of S sub 0 equaling a particular state X, given that an observation at state 0 equaled A, and I'm assuming here that X and Y are permissible values of a state, and A and B are permissible values for an observation. In this case, we just basically apply Bayes' rule and rewrite this conditional probability of state equal X, given the observation equals A, and we rewrite it this way as the probability of A given X times the probability of X divided by the probability of the observation is A. And so we're just taking this and we're re-expressing it as something that we know are going to be in the probability tables. We know that this probability will be found in this probability table for that node, and we know that this probability will be found in this probability table here, and this probability is not actually found in a table. probability tables here are only going to include probabilities like of this form, the probability of the observational equaling A given the state equaling X. But if my job or my goal is to compute what is the most probable state given the observations, I don't really have to compute this value, because when I take a look at this, I see that this is proportional simply to that. Notice that this is common across the numerators, and so all I really have to compare is this value with this value, and that tells me what the more probable state is going to be. And again, this is just a simple example of what we're talking about up here, in which we're only looking at one observation and we're trying to predict the current state. Here is a somewhat more complicated example that's looking at these two, looking at the belief network or the hidden Markov model up until this point. And what we want to compute here is the probability that S sub 1 equals X given these two observations. Observation at O sub 0 equaling A and the observation at O sub 1 equaling B. This is probably something that I might ask you to do for the assignment for Friday, is to compute some probabilities like this. But again, because you know from last week how to compute joint probabilities and conditional probabilities for any Bayesian network, I hope, you can do the same thing here. And the job is compute the probability of this given the probability of these two things. And what that's going to involve is, again, I'm going to try to compute what the more probable state value is going to be. I rewrite that in a standard way. And again, these are proportional to, I don't have to compute the numerator explicitly to make a relative judgment about what's more probable. You can review this, but the probability of observation B given X can be found in a probability table, but I've also got to compute the probability of S1 equaling X and O sub A equaling A. And in this particular case, if you remember the strategy for connecting, I've got to compute a joint probability between these two values. I've got to connect them in order to access probabilities that are actually given in the network. And the way that I connect them is to sum over all the possible values for the intervening variables. So the probability of S1 equaling X and O sub A equaling A, O sub 0 equaling A, is to simply take a look at the joint probabilities involving that pattern, but also paired with each possible value for S sub 0. I sum over that and I get that value. And again, you know how to do that, or should know how to do it. You'll probably see it in an assignment. You'll certainly see it on next week's exam. So here's a problem in localization that's given in the text. We have actions that we can perform. And in this localization problem, the robot is plopped down in the middle of nowhere. Well, not in the middle of nowhere, but on some grid. And the robot can execute actions and determine the probabilities of where they have been placed. So we might put the robot in location 5 initially, and the robot can execute some actions. The robot is going to look at its sensors. So I put them in location 5 with some probability. They look at the observation that corresponds to that location. They perform some action, and they are in a new location. But they don't know exactly, the robot in this localization task doesn't know the location that they are necessarily in. So they make a a new observation, execute a new operator, another operator, and they are in perhaps a different location, another observation. And so they continue that process, and over a series of observations, over a long series of observations, they can project the relative probabilities of being in each of the possible locations. So if I am plopped in front of door 4 and my observation is I see the door, this is a sensor in this example is whether they see the door or not, that is going to be a occurrence that happens with high probability, but they may go to the right. They may not see the door. They may go to the right again. They may not see the door. They go to the right again. They see a door. They go to the left. They see a door because these sensors are faulty. They have uncertainty associated with them. But if that's the case, if that's the example we used, with high probability, door 7 might be, or door 6 in this case, might be much more probable, say, than door 10 or door 9, given those series of observations, even when there's uncertainty associated with them. So that's the job of localization. It is an example of this process that we were talking about that is inferring states given observations only. And again, you've got to specify all the appropriate probabilities here. The book talks only about probabilities for the sensor models. What are if the robot is actually at the door, and we're talking about these observation nodes right here, the probability, if the robot is actually at the door, what's the probability that they will observe the door? Let's say it's 0.8. And you can compute from that the probability that they won't observe the door, given that they're at the door. The probability that they observe the door, given they're not at the door, is 0.1. The inverse is 0.9. Now notice this is sort of generalizing this probability a bit. If we were to, you could use this representation of probabilities, but if you were to represent these probabilities as we have been doing in the past, we might actually specify a probability that they observe a door if they're at 7, the probability they observe a door if they're at 4, the probability they observe a door if they're at 2. Given what we have discussed so far, that's the way you would represent these sensor models. Okay? The possible values would be 0, 1, 2, 3. They would be cell numbers in effect. And so you'd specify at each location here, or at each, in the probability table, you'd specify the conditional probability that a door was observed at 0, a door was observed at 1, at 2, at 3, etc. Okay? So the book is taking a little shorthand shortcut here with this at door probability representation, but it actually is suggestive of some ways that we could improve some of the systems through learning later if we chose to. So it's not a bad thing, but just recognize that the way that we've been doing it so far, we would specify different probabilities for each of these. And just like we had different weights in the Othello game that we talked about with adversarial search, you might actually have different probabilities. There might not be one probability of observing the door if you're abstractly at a door, but it might be more likely that you would observe doors in the vicinity of doors. So it might be more likely that you observe a door here than you would observe a door here. Okay? And so there could be also some advantages to to those separate probability assignments for each cell. And then you've got transition probabilities that associate if an action was taken and you were at a particular location, then you'll be at some new location with some probability. Notice that there are no probabilities assigned to these nodes. The example that the book is talking about is a little bit misleading because a lot of the language is talking about a robot that is proactively taking actions. But a better way to think about this is this is describing a system in which somebody is observing a robot behaving, observing a robot taking actions. Given that, we would assign probabilities to, we would have probability tables for each of these nodes as well, because this is just a Bayesian network. So the probability of the robot executing some action, say pick up coffee, is 0.3. Probability of another action, move to the mailroom, is 0.2, et cetera, et cetera. And we would have the probabilities assigned for these nodes as well. Where these actions are going to be important is in the next chapter. And we'll probably talk and revisit this on Thursday, but a couple of important things that we saw in the lecture from last Tuesday on inference with belief networks was, one, the idea of conditional dependence. And we saw situations like this. If I know a location, that induces this says that an action is independent of a prior location given the current location. Okay? Seems a bit counterintuitive since this action is listed as action sub 0 and presumably is going to be picked because I'm in a location 0 and I make an observation 0. One would think that in the natural model, that action would be selected because I was in a location and I made a particular observation. But this says this is independent of this, conditioned on this. But again, we might return to this on Thursday, but if you remember the lecture from last Tuesday, there was this concept of conditional dependence. If I know that value, then that induces a conditional dependence between these two values. And that's actually not as important as a second observation that we haven't gotten to yet. But we also touched on the important concept in last Tuesday's lecture. When we set conditioning information to be a particular value, you might remember from Tuesday's lecture that if this was set to a particular value, it was if that the probability of that setting disappeared from the calculation of the probability of what we were trying to compute. Setting that to a particular value would eliminate it from being referenced in the probability here, okay? Because we set that value, we set this variable to a particular value, it's as if we set the value or the probability of that particular value to 1. And so it didn't play a part in the computation of a conditional probability here. And so that will become important later because in chapter 9, the robot is actually selecting what to do. And it's as if the robot is proactively selecting a particular value for this. And that term will sort of disappear in the computation for the probability of this state. Again, you could probably go back and look at that lecture and find the place I was talking about that. It was early in the lecture, but we'll probably revisit it on Thursday. So this idea of we can have multiple observations for each location. This is a door sensor and a light sensor. Nothing particularly tricky here. Location, sensor value, setting or observation is independent of the door. Sensor observation conditioned on location. You can fill in these probability tables perfectly fine, and do reasoning with two sensors versus one sensor. And you can, of course, have multiple sensors there. Language is discussed in this chapter, and it's interesting. It's the only place that we'll actually talk about language processing. But language sentence structure and generating sentences can be viewed as a Markov model, or at least a sequential model. Here is what's called a bigram. This is essentially a Markov representation of generating a sentence in which the first word of the sentence is followed by a second word, is followed by a third word, followed by an nth word. And we would essentially, in this model, define transition probabilities between a prior word in the model to a subsequent word in the model. The Markov model is way too simple, I think, for true language competence, but nonetheless, it can get you a kind of long ways. I think I'm going to actually skip this too, but we have talked about the naive Bayesian classifier, and I think we've actually mentioned briefly that we can represent that as a sort of as a Bayesian net. Remember, in the naive Bayesian classifier that we discussed at some depth under the machine learning lecture, is that the variables that are used to describe objects, the variables are conditionally independent of each other given the classification. This is a simple example of, and so if you want to compute the values of a conjunction of words, in this particular case, or using the naive Bayesian classifier, it's going to be the probability of a particular value for this variable times the conditional probability of a particular setting for this variable conditioned on H times the conditional probability of a value given here, given H, etc. Okay, so you can review the naive Bayesian classifier slides, but the very simplest language models might view language in terms of naive Bayesian classifier. And this might be a model that's used in this example to distinguish between help pages for various things. So you're going and you're asking for help in a website, and the words that you choose are going to be used to distinguish which of the many help pages might be under that help tab of the page. And again, the intelligence of that system that is directing you to one help page versus another help page is could be represented as a naive Bayesian classifier like this. Sets of words, I'm going to skip a couple of these. This is a common representation for documents is simply a bag of words, or sentences as a bag of words, just a collection of words, unordered. If you want to reason about sentence structure, or the words that are going to be in sentences, you would specify the probability of various word occurrences within a document. I interpret sentence very literally, or very liberally, as any kind of structured text. And very often this bag of words approach is used for documents. So if I, for example, want to judge the similarity between documents, the representation for the two documents that I'm considering is just a collection of the words that are in those documents. So you take the two documents and you remove all sentence structure from them, and you just create a unstructured set of words. Actually a bag, because you keep repeated words. And you compare the similarity between two documents, and you compute that as simply, intuitively, the overlap in the words that are used in those two documents. It actually is remarkably effective in some cases, even though it removes all structure other than the occurrence of words. Again, this is a bigram model, something that corresponds to a Markov model. A trigram would, if you're trying to piece together or generate sentence structure, the next word that you might select would be based on the last two words, not simply the last word. You can generalize that still further to an n-gram structure, and so you might have a considerable phrase here, or memory history of prior words used to generate the next word in a document, or to recognize the next word in a document, or to anticipate the next word in a document. And anticipation is important in predictive typing and error correction. However they're doing it, they're not doing a very good job, but this is a structure that you might use for representing that. I'm not going to go, you can look at the book for more details about these two things. I just want to briefly mention topic models. This is the way that a belief network might look for a topic model. Topic models is a representation of topics that are found in texts or documents. So tools, finance, fish, food, these might be regarded as different topics. And these are connections to words that are found in documents that are associated with these topics. So for example, bolt and nut might be highly probable. If we were to take a look at the probability tables here, the probability of bolt, given that we were talking about the tools topic, the probability of bolt might be found in a document with this tools topic might be relatively high. The probability of nut being found in a document on finance with a topic of finance might be considerably lower. I don't know if the authors were trying to be funny or not, but that's a representation. The probability of words are regarded as independent, conditioned on their presence in a topic or topics. So here's an example of how you might use topic modeling. This is just an analysis that we did of courses that are on computing and sustainability. And all of these courses are seminar courses. So they require that the students read lots of papers from journals, paper from conferences. And so one thing Zime, Celine, and I did is we took all the documents from all the computing and sustainability courses that we could find a while ago. And these are sort of early papers. We took all those documents and we put them into a single set. So at Bryn Mawr, they do some reading. At Vanderbilt, we do other reading. Cornell, still other reading. And you put those in a collection of documents. So what topic modeling software will do, and the topic modeling software we used was out of the University of Massachusetts at Amherst, a system called Mallet, is you feed a collection of documents, ideally a large collection of documents, to the topic modeling software, and it will identify common topics within that document collection. So for example, this has been used to classify articles from science and nature and whatnot. So you might throw all the articles from Science and Nature for the last 20 years into a topic modeling as input to topic modeling software. And ideally, the topic modeling software would distinguish topics like biochemistry from astronomy, from some type of behavioral science like psychology. And it would identify these topics. And if you asked it to, it could drill down. It could identify various kinds of psychology. It could identify various kinds of chemistry, various kinds of biology. But it associates with the topics. The way it represents topics is, of course, it doesn't give names to topics, but based on the associations, based on it breaks these into topics based on more or less similarities between the topics. It's a kind of unsupervised machine learning. And it identifies sort of the major keywords associated with each category or each topic that it is identified. It's up to then some user, some expert to assign a topic name to each topic. And so these are the set of topics that were generated from the set of all papers in these various computing and environment courses. And then if you take a look at each, then what we can do, and this is the most interesting, one of the most interesting things, is we can take a look at the documents from each course taken all by itself, and we can identify, of the topics identified, what were the most dominant topics within the Bryn Mawr course. And we can go back and look at those topic names. Topic 1, optimization of a particular kind on sensors was one dominant topic. Another dominant topic was topic 2 on urban policy. And these can be contrasted, these dominant topics can be, say, contrasted with the readings that we did at Vanderbilt. You compare these and the dominant topics seem to vary quite a bit. No overlap in dominant topics between these two courses. But I think that's an interesting functionality you can use with topic modeling. It is not, however, related much to sequential reasoning as the type we've talked about.